Okay, so this is the lesson for section P3 on radicals and rational exponents. You'll notice everything in this chapter P, especially in module 1, is the prerequisites chapter. So these are fundamental concepts from algebra 1, algebra 2. These should be familiar to you. So nothing that we're learning really this week should be new. Maybe it's familiar and you need a little bit of a review. So even when we talk about this lesson, I'm like gently reviewing these concepts. I'm not teaching them from the ground up because hopefully you should be pretty familiar with them. If you have questions, though, obviously let me know. In this lesson, we're going to be tackling a bunch. I'll give you guys a second to read that list. Handling a lot of things with square roots and rational exponents. That is the theme for today, this lesson. Okay. Okay, so let's start off with the general definition here of a square root. And really, it's this basic sentence at the very top here. We need to know and remember b squared equals a. So if b squared equals a, then b is the square root of a. So when it's these two, we need to remember that when we square something, and then if we take the square root of something, these are inverse operations. So b squared equals a, and then b equals the square root of a. They're inverse operations, they undo each other. That's the principle, square root rule here that we're going to talk about and use throughout this class in today's lesson. So some review problems. So the square root of 81, very simple, right? Square root of 81, we know that's 9. We're looking for two numbers that when you multiply it by itself, it equals 81. So 9 times 9 equals 81. Negative square root 9, that negative is on the outside, so we're going to keep it on the outside. Square root of 9 is just 3. Okay, so my answer is a negative 3, only taking the square root of what's inside under the radical. And then we've got the square root of 36 plus 64. We can add what's under the radical, so we're going to get the square root of 100. And then I know I can simplify the square root of 100, and that's going to give me 10. Basic review of square roots. Pretty straightforward. And now let's tackle this product rule. So the product rule for square roots tells us that if we see two terms being like that are multiplied together under a radical, we can separate it. So the square root of a times b equals the square root of a times the square root of b. And also, if we see two radicals multiplied together, we can put it under one radical. We can combine them. Does it need to be the same variable? They don't need to be like terms. We can combine them like this. And so an example of this product rule, let's check out these two examples. So we have the square root of 75. So that's one term, that's one number, square root of 75. And if I can break this up and think of two numbers that multiply to 75, in particular where one is a perfect square. So if I think about 25 and 3, that is a true equation because 25 times 3 equals 75. So I can rewrite the square root of 75 like this, the square root of 25 times the square root of 3. And it's great for us to rewrite it like this because now I know this is easy to simplify. Square root of 25 is 5. Square root of 3 doesn't break down anymore. So I know that this is the fully simplified form, 5 square root 3. The other way to use the product rule is in this example. And in this second example, we have two radicals separate, and the product rule tells us that we can combine them. So now I can rewrite this as we can do 5 times 10, that's going to give me 50. X times x gives me x squared. So I can combine the two radicals, and then I'm going to further simplify this And I'm going to use that product rule again, and I'm going to break down the square root of 50. So the square root of 50, if I break that down using two radicals, coming up with factors of 50 where one is a perfect square, we're going to get 25 and 2, right? 25 times 2 gives me 50, and I still have the square root of x squared. Easy, it's best for us to break this down like this because now I can see, okay, square root of 25, that's going to give me 5. Square root of 2 doesn't break down anymore. And then the square root of x squared is just going to be x. And there's my final answer. Okay, so that product rule really helps us simplify square root problems. The next, so that's product rule. Let's talk about quotient rule. It's very similar. Notice here's the two equations here, the general forms. I have the square root of a over b can be rewritten as the square root of a over the square root of b. And then also if I see the square root of a over square root of b, I can also rewrite that as the square root of the whole fraction. And then we'll check out two examples about the quotient rule. Here we go. Okay, so notice in this first example, we have the square root of 25 over 16. And at first, when you look at that, you're probably just focusing on the fraction 25 over 16, thinking that doesn't reduce at all. How am I going to know what the square root of 25 over 16 is? And I don't need to think about it that way, because if I use the quotient rule, we can rewrite this as the square root of 25 over the square root of 16, and think about the numerator, and then I think about the denominator, because then I know the square root of 25 is 5, and then the square root of 16 is just 4, and that's the fully simplified form. For the second one here, it's already broken up that way, and so let's continue to just focus on the numerator and then focus on the denominator. So if I look at the square root of 150, I'm going to break that up. I'm coming up with factors of 150 where 1 is a perfect square. So if I think about 150, I know 25 and 6 multiply together to give me 150. And then I'm going to have the square root of x cubed all over the square root of 2x. Doesn't simplify. And so now I can simplify the square root of 25 gives me 5. The square root of 6 doesn't break down. I'm going to write it like that, square root of 6. And then the square root of x cubed, we can write it like this for right now, and then over square root of 2x. And as we're looking at this, we can start to think I can simplify and break this down further because I have a 2x under the radical in the denominator, and I have a 6x cubed in my numerator. Something looks like we can continue to break it down and cancel. So let's go ahead and let's rewrite the square root of 6x cubed. And so we're going to rewrite that as the square root of x cubed. And then we're going to have square root of 6 is going to be square root of 2 times square root of 3, all over square root of 2x. And so now we know the square root of x cubed, we know that we have 5x times the square root of x. And so what we want to think about is the square root of x cubed. We know that's the same thing as the square root of x times x times x. So if I'm looking for square roots, I can take 2 out, and that's how it becomes that 1x in the front, and then 1x is still left over under the radical. And so I also have the square root of 2 here over the square root of 2x. And now I can cancel, oh, and I still have the square root of 3. And so then we can cancel the square root of 2x, the square root of 2x. And so we're left with, in the numerator, 5x square root 3. Lots of steps there to simplify. And then this is a whole separate review in and of itself with the variable under a radical. Another like a short way to remember it is if you divide the index with the square root, so if you do with the exponent, if you do 3 divided by 2, you'll get 1.5. So one whole x comes out front, and then the other one stays in the radical. Just a little bit of like a way to remember how you break down the variables under a radical. Okay. The next thing we're going to talk about is adding and subtracting square roots. And so in order to add and subtract square roots, we need to have like radicals. So the radicals need to be the same. They need to be the same number, variable, and index. That index is that number, like this is the square root of x. This is the cube root of x. That index is this number right here. Okay, so if we add 8 square root 13 plus 9 square root 13, because these are like radicals, we can add these two terms together. All we need to do is focus on the numbers in the front. So I know that this is 17 square root 13. And that's all that can be done with this problem. To subtract, I can subtract these terms because they both have the square root of 17x under the radical. And so I know that this is a 1 times square root of 17x minus 20 times the square root of 17x. And we can subtract this 1 minus 20. That's going to give me negative 19 times the square root of 17x. And that would be my fully simplified form. The next concept that we're going to talk about is rationalizing denominators. So rationalizing denominators is the process of making sure we do not have any radicals left over in the denominator. We are not allowed to have radicals in the denominator in math. It's bad math, so we need to figure out how to get the square root out of the denominator. And so this is the process of rationalizing denominators. What we need to do is multiply the numerator and denominator by the smallest number that produces the square root of a perfect square in the denominator. And what that number is the conjugate of the denominator. And I'll give you a second if anyone's writing that down, and I'll slide down to the next page. But rationalizing denominators is really important so we can write fractions or terms without radicals in the denominator. And so conjugates is going to help us make sure we don't have any radicals in the denominator. Conjugates are, if we have two terms, we just change the sign. So if this was in your denominator, this is its conjugate. It's the exact same thing. One's just positive and one's negative. And this helps us rationalize the denominator. I can give you some examples. If it was like 1 plus the square root of 3, let's say, if the fraction was like 5 over 1 plus square root of 3, the conjugate is 1 minus square root of 3. And you'll see, I'll show you the example. Multiplying by the conjugate helps to remove this square root in the denominator. And so let's check out a few examples here. Rationalize the denominator of 5 over square root 3. So what we need to do is we're just going to multiply by that denominator. If it's just one term, we're going to multiply by that denominator. So I'm going to multiply the numerator by square root 3 and multiply the denominator by square root 3. 5 times square root 3 is going to give me 5 square root 3. Square root 3 times square root 3, we multiply the radicands, so I'm going to be left with square root 9. And then I see 5 square root 3 in the numerator, nothing simplifies. Square root 9, I know that's 3. And so notice this form of that fraction is in way better form because I don't have any radicals in the denominator. So we have rationalized the denominator. Let's do the same thing for the second example. Notice now I'm going to use the conjugate of the denominator because we have two terms in the denominator. We have an expression in the denominator. So I'm going to multiply the numerator and denominator by 4 minus square root 5. That's the conjugate of the denominator. And so we're going to do some multiplying. In the numerator here, we're going to distribute that 8 to everything. So we'll have 32 minus 8 square root 5. In the denominator here, we are going to have to FOIL or multiply, distribute these two binomials together. So we'll have 4 times 4, that gives me 16. 4 times negative square root 5, we'll have negative 4 square root 5. Square root 5 times 4, 4 square root 5. And square root 5 times negative square root 5, we'll have negative square root 25. And so notice what happens, and hopefully you don't need to write out that whole FOIL every time. So my numerator, we're going to keep as 32 minus 8 square root 5. Notice in that denominator, we have some things cancel. Negative 4 square root 5 plus 4 square root 5. Those two terms are going to cancel every time. That's why I said hopefully you won't need to multiply and write out that whole FOILing. And then we know that this is 5. So I have 16 minus 5. That's going to give me 11 in the denominator. And so our final answer there will be 32 minus 8 square root 5 over 11. And that's a way better expression, way better final answer than this, because I don't have a radical in my denominator anymore. Okay. Couple more topics today is being able to simplify radicals of higher indexes. So notice these are cubes. Okay, so I've got the cube root of 40 instead of the square root of 40. And so there's a couple ways you might have learned how to do this. I'm just going to review it with a factor tree. And so a factor tree, if you remember, will have like this, that number up here. And we're going to break it down using factors of this number. So 40, I'm thinking about 2 and 20. And then I'm going to break down 20, and I'll think about 5 and 4. 5 can't be broken down anymore. 4 is going to be 2 and 2. And so when we are now breaking this down using the cube root of 40, cube root tells us that we're looking for triples. So if it was the square root of 40, we look for pairs, doubles. I'm looking for 3 of the same number, which I have. And that number comes on the outside of the radical. And then anything that doesn't have a triple or a other of the same number stays on the inside of the radical. And so our final answer is going to be 2 times the cube root of 5. I'll show you again with the second one here. So again, using that quotient rule, we know that this is the same thing as saying the cube root of 125 over the cube root of 27, right, using that quotient rule. And then cube root of 125, well, that is a perfect cube. That is going to be 5. And then the cube root of 27, that is another perfect cube. That's going to be 3. So I've got 5 over 3. Didn't need to do a factor tree for that one. And then this last concept that we're going to talk about today is if we have a rational exponent. So notice this is a couple different forms that we want to jot down, rules that we'd want to jot down. If we have a fractional exponent, so like this, a to the m over n, we know we can rewrite that as a radical. So notice what happens, and these are both the same. Notice what happens is the denominator, so it would be good to write down the denominator becomes the index. Is the index, and then that numerator becomes the exponent. Okay, and so that's how we convert between a term with an exponent, and then we write it as a radical. And we can bounce between the two forms, always remembering that the denominator is the index, the numerator is the exponent. Obviously, if we have a negative exponent, we can do the same thing. Yesterday's lesson, P2 lesson, this morning's lesson, that if you were here on Zoom, we talked about if you have a negative exponent, you can move it to the denominator and it will become positive. And so that's what this general form describes below. We will look at 2 examples of this, and then we'll be done. Okay, so using that rule of a fractional exponent, let's simplify 27 to the 4/3. So let's rewrite this as a radical. We're going to have the cube root of 27 to the 4th power. So notice when we look at this, I don't know 27 to the 4th power in my head, right? 27 to the 4th power is some large number. But I do know off the top of my head the cube root of 27. So we can do that first, right? The cube root of 27, that gives me 3. And then I still have to raise that to the 4th power, which is going to give me 81. Okay, and so that's where like you can handle the radical first and then apply the exponent to it. That's what these parentheses represent. And then our final example using this, we're going to do something similar. Actually, I don't know. I don't think so. We're just going to simplify using properties of exponents. So we're going to focus on like terms. I like to do the 2 times the 5 first, so that's going to give me 10. And then remember, when we're multiplying variables, we add the exponents. So I'm going to have x to the 4/3 plus 8/3. So that's going to give me 10 times x to the 12/3, 12/3, which is going to give me 10 times x to the 4th power. So that was just a practice problem simplifying expressions with rational exponents. So that's our lesson for P3, all about rational exponents and radicals. If you guys have